Okay.
Okay.
Okay, where it is?
You should put Victor as co-host.
No.
Okay.
No, it's not this one. Where is? Now I cannot find my.
Present.
Now okay. I have to put my something wrong with all this. It's impossible. I'll try.
You have to put more credit to Skype.
Okay. Do you see? No, you cannot see. I escaped. Okay. Do you see? Do you see a screen? No.
Yes,
yes,
we
I
can
see.
Okay, it's good, but not very good. I have to put it to make it more more.
Full screen.
Yes.
Or wider. Okay, it's okay.
Do you see?
Yes, it's okay now.
Is it good? Okay. Okay. So it is okay. Let's start introduction. But you see, now I see only experts, so it's not necessary to to give introduction. Alessandro wrote me that some young people will be here, yes. But as I understand, now we only experts. You see.
Yes, I agree. So you can skip or be fast in the introduction. But remember, this is going to be it is recorded, so maybe young students can watch it offline.
Okay. Originally, the equation, the BFKL equation, was derived in non-abelian gauge series with spontaneously broken symmetry. It was done in 1975. And this series with Higgs mechanism of mass generation was used to escape infrared singularities. And but then it was recognized that the equation can be used also in QCD. So, and of course now the main application of QCD is of BFKL is just QCD. You know that BFKL equation became famous due to discoveries of rapid growth of gamma star E cross section at Hera, and we see usually BFKL associated with evolution equation for unintegrated Greuel distribution. Partner distribution are necessary parts of modern description of process with hadrons, because this process, of course, at hard scale, hard scale is necessary in order to use perturbation theory, because of asymptotic freedom, coupling constant at hard scale is small. It's possible to use perturbation theory, and cross section can be written in such form of convolution of Parton distribution with hard cross section, partonic cross section, and of course. Evolution equations. Evolution equations are called now Nucl equations, not in opposite order. Nucl, and they have such form. This evolution equations, in sense, they are Renorm group equations, and so the kernel of this equation or part of splitting functions can be calculated perturbatively in any order of perturbation theory. Now they are known in three-loop approximation and partly in four-loop approximation. And but what is important that this equation some large logarithms of q squared. Q squared is supposed to be large, and logarithm also, it is a parameter of perturbation theory, one of parameter. And but there are another logarithms, logarithms of 1 over x, where x, it's Bjorken x, is q squared over s, and at small x, it's necessary to sum up also such logarithms of 1 over x. And there is a resummation of these logarithms is performed just by the BFKL equation. BFKL equation, okay, well, it's not seen, I don't understand. No. Oh, sorry. Okay, it's not the screen now is too small. Okay, maybe it is better now. All letters are seen. So, but it's too. Okay. So, as I already said, that BFKL equation sums log 1 over x. In leading logarithmic approximation, it is summation of terms of alpha s log 1 over x in power n with arbitrary n, and but in the next to leading terms with one extra alpha s and so on in principle. But now this equation is written. The kernel of equation is known in for leading order and next to leading order. In the leading logarithmic approximation, equation predicts some such growth of cross section, and of course it's not good because such growth violates the very famous Frossard limitation. You see, there is power growth, but it's impossible. Cross-section can grow only logarithmically as square of logarithm square. So, of course, it's necessary to improve such behavior, but just you see, of course, the Frossard limit of growth is strictly speaking, it is asymptotical requirement, asymptotical restriction. And now you know that the cross sections of not only gamma star P cross sections, but also PP cross sections grow faster than Frossard bound. So in principle, it is it's modern energy. It's not suppressed. It's not forbidden. But of course, asymptotically, such behavior is forbidden. But as I already said, the equation became famous just to rapid growth of cross section gamma star P cross section. But really, region of applicability of the BFKL approach is much wider. Moreover, the approach was developed and is more suitable for description of processes with only one hard scale, such as gamma star scattering, and both photon virtualities of the same order. Okay, it is rather known things, but I already said that growth violates the Frossard bound, and it's necessary to understand that this problem cannot be solved by calculations of radiative corrections at any fixed NNL order, and requires other approaches, other methods. The most popular now are nonlinear generalization of the BFKL equation related to the idea of saturation of parton densities. The idea appeared rather early, not long after the appearance of the BFKL equations, BFKL equation. But there is another approach It's can be said that it is a general approach to the unitarization problem. This approach is so-called gauge invariant effective field theory for exercise-gluon interaction. But in principle, it can be used, but it's not easy to use it also. Now, how the equation appeared. I told already that the equation is result of summation of radiative correction to scattering amplitudes. In any order of perturbation theory, the equation was written for elastic scattering amplitudes, but it was derived using dispersive approach. That means, but this approach is based on general properties of analyticity, unitarity, and renormalizability. Of course, it is very general basis. It is good, but of course, it is. You understand that it's impossible to calculate amplitude, even elastic amplitude, in any order of perturbation theory. But the approach based on unitarity, in this approach, it's necessary to know amplitudes in all order of perturbation theory, not only elastic amplitudes, but amplitude with production of arbitrary number of particles, arbitrary number of partons, because in unitarity relations for elastic amplitudes, it's necessary to use amplitudes for production of arbitrary number of particles. And of course, it's impossible to calculate of all such amplitudes. Of course, it was necessary to have some idea for calculation. And this idea was the gluon regization. The gluon regization and in general regization of elementary particles is one of remarkable properties of QCD. Maybe you know, maybe of course not. I mean, students maybe know that in quantum electrodynamics there is regization of electron. Electron does regize, but photon not. But the QCD is very special theory in which all particles do regize in perturbation theory. And of course, gluon regization is very important because it determines high energy behavior of cross-section non-decreasing with energies. So due to the realization, we have a very simple form of elastic scattering amplitude. You see, this amplitudes have such simple form. Here we have vertices, here vertices for scattering vertices or part-and-part region vertices, particle region vertices. And here we have regicide gluon propagator, where you see what is difference with Born approximation. The difference is that we have, in fact, in Born approximation, amplitudes have the same form, but the difference is only this vertices are very simple. It's simple. It's some kinematical factors, only kinematical factors, only constant, in fact. And here also we have the same form, but J over T equal unity. Unity is the spin of gluon, spin of gluon. You see difference only that we have for retrons, we have more complicated vertices. But I have to say that in the leading logarithmic approximation, these vertices simply Born vertices, simply vertices in the Born approximation. And another, and maybe it is the main difference. The main difference is that we have unity here. We have J on T, which is so-called gluon region trajectory, or regized gluon trajectory. It is usually written in such form where one is just the spin of gluon spin of gluon. Okay, and you understand that if we assume the regization, that is quite easy to calculate amplitude, but I want to say that it is amplitude in the leading logarithmic approximation, and really in the next to leading. The leading amplitude are amplitude with gluon quantum numbers in T channel. That means gluon quantum numbers. What does it mean? What means gluon quantum numbers? Scalar. It is scalar octet in the T channel, and negative signature. Signature is symmetry with respect to such exchange. And why negative? You see that we have here negative signature because J negative signature because J you see that J in the Born approximation, J is 1, and at J over T equal 1, we have the antisymmetry here. When we when we expand this you see, perturbation theory means expansion in terms of omega over T multiplied by log S. And when we have minus sign here, we have the leading terms doubled, while plus sign they cancel. Leading log terms cancel in each other. And so the leading amplitude are amplitudes with negative signature. Negative signature. It is important. Negative signature. And negative signature, in fact, it means gluon exchange. Gluon exchange. So something like this occurs amplitude, in elastic amplitudes. They can be represented by such pictures. Again, we have here the same vertices as before, elastic vertices, and here we have new vertices, production vertices, which were calculated firstly by Lipatov, and they are called very often Lipatov vertices. You see this vertex, such representation, again, here vertices, scattering vertices, here production vertices, and here gluon propagators. But what is different with respect to this picture? Here you see we have really here in this formula we make distinction between this this term and this term, but you see the distinction only in phase. These terms have equal modulus, but different phases. That means, but dominant pieces here is real parts, and imaginary parts here are non-leading, subleading, because in imaginary parts, you see, when we write log s, we have log modulus s, which is big value, plus I argument s, which is not big, not large. So the most important part is real part, and here you see it is written only for real part. The reason is that in fact imaginary parts very complicated. In fact, they are very complicated. I want to see that analytical properties of elastic amplitudes, very simple analytical properties of elastic parts, but analytical properties of inelastic amplitudes rather complicated. It's possible to say that they are very complicated, in fact. And in fact, I can say that first, you see, originally, when the BFKL equation was derived, we did not pay attention on imaginary part, because imaginary part of inelastic amplitudes, because they are not important for derivation of the BFKL equation, because in the unitarity relations which were used for derivation of the BFKL equation, only real parts of inelastic amplitudes are important. Only real parts of inelastic amplitudes are important. Moreover, even more, that even in next to leading logarithmic approximation, also only real parts are important, even in the next to leading logarithmic approximation. And it was the reason why we don't pay attention on imaginary parts. But I don't remember exact year, but I suspect it is in 2008. Bartis, Lipatov, and Sabia-Vera, if I not right with the date, Augustine will improve me. Augustine.
It's good, it's good. It's good. 2008.
They paid, you see, with connection of BDS, BDS formula, BDS ansatz for amplitudes in maxima n equal 4 super young mills. You see, there was there was BDS formula, which is BDS means how was the first I don't I forgot, sorry. Bern, Dixon, and Smirnov. Yes, they suggested formula for all orders of perturbation theory, which, in some sense, which summarize all singular pieces in not only singular, but let's say singular pieces in n equal 4 super young mills. But the Bartels, Lipatov, and Sabia-Vera paid attention that this formula contradicts the BFKL approach, and really they investigated in more details that imaginary part of these amplitudes and discovered that there is a region cut in, but in this in imaginary parts, in imaginary parts of amplitude with production of 2 or more particles. But it is too far from our aim to discuss this. Maybe Augustine will give another seminar, I don't know. But now I have to continue, and I repeat that it is a formula for only for real parts. And you see, when we have formulas for all inelastic amplitudes, we can calculate imaginary part of elastic amplitude. It is using unitarity relation, and evidently it is a representation of S-channel discontinuities, and then the discontinuity can be presented in the form of convolution of impact factors of scattered particles, and green function of two interacting reduced gluons. So it is, and BFKL equation is just the equation symbolic for this green function. It can be written symbolically. Equation can be written as derivative of the green function when is equal some kernel multiplied the green function itself. Y is, let's say, rapidity. Is this logarithm, which is called often called rapidity, and it is the kernel of BFKL equation. And because this, we see that this amplitude contained of have such form, it's easy to understand that the kernel can be written as sum of trajectories of interacting gluons and some real part, which real part it is the piece which comes from vertices, product of production vertices. When in the leading logarithmic approximation only gluons can be produced, so it is simply product of convolution, let's say convolution of vertices for production of one gluon. At the next leading approximation, two gluons can be produced in with approximately in the same region of rapidities, or quark-antiquark pair can be produced with approximately the same rapidities. So the kernel has such form, and it is energy dependence is determined by BFKL kernel. So it's the most important thing is the kernel of the BFKL equation. It's necessary to say that the separate pieces of the separate pieces, I mean trajectories and this is production, real part of the kernel, they are separately, they are infrared divergent, and only in the sum there is conservation of the divergences. And in the next leading approximation, the kernel is rather simple. You see, it's rather simple, not only for forward scattering, but for scattering at arbitrary momentum transfer. But in the next leading approximations, rather not very simple. It is written here for forward scattering. It is much more complicated for non-forward scattering. It is also known now. It was calculated also, but I present here only for forward scattering. It's not very simple, not very complicated. It's can be presented in such form. It's, of course, it is there's no sense to pay much attention, but what is may be important, it is this next to leading accuracy when we have running coupling already. Running coupling, we have some in some sense intercept. Of course, intercept now depends on Q squared because running coupling depends on Q squared. In such way, you can write the intercept, and it is contribution of leading order and next to leading one, and it occurs that the coefficient rather large. The coefficient rather large. If to write this correction and these corrections in such form, it is all simple alpha s number of colors, and it is intercept in leading order, and this coefficient, you see, this coefficient is rather large. So correction is very large. It is of course problem. Now there are some ways of treating of this problem. I cannot explain them. Have no time, of course, to explain them. What another result, interesting and maybe important result, which you obtained in the BFKL approach. The interesting result is that this representation can be used for finding. It can be used also for finding eigenvalues not only for leading, but also for not also for forward case, but also for non-forward case, and they can be used for connection between the eigenvalues of BFKL kernel, eigenvalues of BFKL kernel and anomalous dimension, which I used in the Nucl approach in some sense, and can be used in N equal for super young meals. For then it's now the analog kernel is known also for T non-equal 0. It's shown that the kernel can be written in the conformal invariant form, not completely conformal invariant, but in the form which conformal invariant is violated only by the renormalization. The next interesting result is that it's possible to find, using the BFKL approach, it's possible to find the remainder function to the BDS ansatz. I already told that the BFKL ansatz is not correct, that it is violated for the production of more than 2 particles. So of course, many interesting results were obtained in the BFKL approach using the BFKL equation. many interesting results were obtained, and here I mentioned only about the result for pure theoretical results, but of course there are many results which you obtained for phenomenological description, in phenomenology, for description of experimental data in hadron scattering. But I am not, in fact, specialist here. Of course, Alessandra and Augustin can say much more than me about this use of BFKL approach. Now I want to say some words about justification. That means what I want to say, that the equation, how the equation was written. It was written using the idea of the regization. And I already started to explain that if we assume the regization, if we assume that we have the regization, then it's very simple. It's very simple to write the BFKL equation in the leading approximation. It's not so simple in the next leading logarithmic approximation, but also it's not it's not I can say that it's not easy, but it's not too difficult. At least it is possible. At least it's possible to perform by hand all calculations. Because the reason is that you see that, for example, to write the form of elastic amplitude, it's necessary, I told already, that to calculate the vertices, it's necessary to know only Born approximation. To calculate the trajectory, it's necessary to calculate the first order logarithmic correction. So it's not very difficult. Then we need two inelastic amplitudes. In inelastic amplitudes, only new piece appears. Region gluon vertex. But again, this vertex can be calculated, can be found in the Born approximation. So it's quite easy to obtain only all necessary pieces for construction of the BFKL equation. In the next two leading approximation, it's not so easy, of course, but it's doable. But it is all assuming the gluon regization. Of course, the regization must be proved, and of course it's another. It's another thing to the proof of the gluon regization. How it can be done? This proof. How it was done? It was done using the so-called bootstrap requirement. Compatibility of the regized form with the S-channel unitarity. This requirement is very simple for elastic amplitude. For elastic amplitude, you see we have here it is hypothesis of the regionalization that amplitudes have such simple form, you see, and it is the result of BFKL approach. The same amplitude can be calculated using the hypothesis of the Green regionalization, but of course not only in the for elastic amplitude, but for inelastic amplitude also. But nevertheless, we have here this representation, and these two pictures must give equal results. So it is the bootstrap. It's very simple, of course. For elastic amplitudes, it's not so simple, but for inelastic amplitudes. But nevertheless, it's possible to write this bootstrap relations. And you see, of course, relations. What is necessary to understand that we have this bootstrap requirement, you see, it must be fulfilled. These amplitudes must be equal. These amplitudes, assumed amplitudes and calculated one, must be equal in all orders of perturbation theory. So in principle, it is it gives us in each order of perturbation theory some equation, and then we have a requirement for inelastic amplitudes. We have infinite number of amplitudes, and for each amplitude we have infinite number of amplitudes. It is of course it seems that it is a miracle that all these amplitudes could be satisfied. All these equations could be satisfied, but in fact, all this, you see, it occurs that it's all infinite number of equations can be reduced using to finite numbers of equations for region trajectories and vertices, and this all these equations were proved to be satisfied. Of course, it's important results, but this result, of course, this result was obtained only in the leading and next to leading approximation. And what is important that so in the leading and next to leading approximation, all amplitudes have simple factorized form, the polar ratio form. But what is important that this form is violated in the next to leading approximation. And in principle, it can be understood from the beginning. But history was not such. Really, we did not think. Our main attention was to obtain the BFKL equation is the next to leading order, and to investigate it and to prove the realization. It's possible to say that we did not pay much attention on next to leading code, but it was observed, it was proved that the pole-Ricci form is violated in the next to leading approximation. How it can be, it was proved, how it was observed. What means next to leading logarithmic approximation? You see, it is in which order of perturbation theory it can appear. It appears already in the two-loop approximation. In two-loop approximation, you see, in two-loop, what means leading logarithmic approximation? Leading means one loop in one odd, one logarithm in one loop. Next to leading, and it means one logarithm, two loops in leading approximation is two logarithms. One logarithm in two loop means next to leading approximation, and constant in two loops is next to leading approximation, next to, and this approximation, next to leading. And this amplitudes in two scattering amplitudes, pattern scattering amplitude in QCD in two loops with constant accuracy were obtained in 1900, as I remember. And this man paid attention that the constant terms in this amplitude violate the pole-Ricci form. But then it was the violation was confirmed in the next to leading in the three-loop approximation. In three-loop approximation, this man observed that, but not in exact amplitude, but in amplitudes which were obtained using technique of infrared factorization. They noticed that also logarithmic terms in three loops violate the Ricci pole form. No, in fact, this violation, of course, was not surprised, but nevertheless, for a long time, explanation of this violation was not, I don't know, wasn't explained. There was no explanation in terms of Ricci theory. There were no explanation of such violation. But the first explanation was done in this work, Lev Lipatov and me. It was shown that this violation can be explained by the three-region cuts. Then this paper appeared, and in this paper also some picture for violation, for some explanation of the violation in terms of Reggie cuts, three region cuts was suggested, but unfortunately this picture is not the same as in our first paper. What is the difference in these two approaches? We started from the Feynman diagrams and calculated and performed calculation and found the pieces which are responsible for the violation of the fold factorization, and then we but in principle in this tulip approximation it's impossible to say that this explanation, this violation can be it's impossible even to say that this violation have relation to region cuts, but it's in order to make some conclusion about the origin of this violation, it was necessary to calculate violation in the three loops, and to investigate energy dependence of this violation. Energy dependence of this violation must be if this violation can be explained by region cuts, the energy dependence also region cuts, energy dependence of region cuts is definite, and so it was necessary to understand does it coincide with the observed energy dependence of the violation. It was calculated, and so it's too long. I think you are all tired if you are hear me till now. But what I have to say that there are now what we have. Now we have two explanations of the different explanation. Both explanations are in terms of region cuts, but they are different. And of course, it's not good. It's necessary to continue investigation, in for loops, and partly it was done in the approach which was started, which was developed by Lev and me, and but it's unfortunately it's not finished. So I have to. I spent too much time, I'm afraid, that so I have to come to summary. And the summary is the following. The BFKL approach gives a basis for a theoretical description of low-X processes. And it was derived assuming the polar Reggie form of ring, and the form is valid in all of those perturbation theory, both in the leading and the next leading logarithmic approximation. However, it is violated in the next to next leading approximation. The observed violation can be explained by the three region cuts, but unfortunately it can be explained. But you understand that it's not it can be explained in by something other, and moreover, there are two different explanations in terms of region cuts. Even in terms of three region cuts, there are two different explanations. So, but further development of the BFKL approach in this approximation requires understanding of three region cuts in QCD. But unfortunately, the theory of such cuts currently is in its infancy. So it would be nice to...
Thank you very much, Victor.
You appeared now.
Yes, yeah, I've always been here. I think we have always been here. But,
okay.
But silent and
It's a pity that you did not comment. Okay, but maybe now you will.
Yes, we can do it now, and I encourage questions or comments by anyone.
Okay, can I start?
Yes, sure.
Just to say, okay, is the situation of the cuts different in QCD than in N=4 super-Young Mills?
Yes, it is different. Yes, it is different. Why it is different? It's different because from the beginning, you know that in the for elastic amplitude, yes, in N=4 super in planar, N=4 super-Young Mills, yes.
Yes.
They, you know, that the BDS formula, yes. Is agrees with the pole retiform, yes.
Yes.
So, and it is known, but it is not proved. But it is, as I understand, common opinion. It is common opinion that elastic amplitudes have no some addition function, yes. BDS formula correct. BDS ansatz correct for elastic amplitude. So it is in some sense common factor, that common opinion that in BDS in N=4 super-Young Mills planar N=4 there is no violation of pole retiform, and it agrees with the fact that the terms which violate the pole retiform, which were found by Glover and Del Duca, yes, and Del Duca with Glover and with Italian people, this violating terms are suppressed and latency. You see? So it is the difference.
So this means that there is some chance to have, there are easier chances to have LLA corrections to BFKL equation in n=4 super Mills than in QCD, or is it, I mean, prohibitively difficult even in an n=4 super Mills?
You see that now there are some, in some sense, not equation itself, but at least eigenvalues of the BFKL kernel are written in in planar n=4 super-Young Mills. They're written in next to leading order. These eigenvalues are written by you see, they are written not in not, you see, not they appear not as solution of the BFKL equation. Yes, in some sense, they are written using using the correspondence between string theory and n=4 Young Mills. Do you know that it is using Maldacena hypothesis? So, but of course, using some hypothesis of how it is called, full integrability of the n=4 super-Young Mills. You see that this, you understand that the integrability of it is also hypothesis. I don't want to put shadow on this hypothesis, but of course it would be very desirable. It would be very interesting to derive the BFKL kernel in the same approach as it was used for in leading and next to leading approximations. Do you agree?
I see. No, I see the point. I see the point. I cannot say that I agree because not enough expert on that to make any comment. So further questions?
So the cat contributions are not inside the class of highest transcendentality functions.
But you see that the principle of maximal transcendentality, yes, it is not for kernel, for the kernel. It is for eigenvalues. But so for the kernel, we cannot use it.
But the cat contributions will give a contribution to the eigenvalues at next to the order.
It is too complicated. It is too complicated thing. You see, now, unfortunately, what is known and what is discussed till now. It is violation of cut contributions to elastic amplitudes, and you understand that elastic amplitudes, you see, they you see that the kernel in the leading and next to leading amplitudes, the kernel was expressed in terms of trajectories, yes,
Yes.
and the real part which is expressed in terms of region particle production vertices, yes. Production, of course, for calculation of trajectory, for calculation of trajectories, cut contributions to elastic amplitudes is important in order to determine the trajectory. It's necessary to know cut contributions to elastic amplitudes, but maybe the most important part is the real part of the kernel, and elastic amplitudes have no connection to real parts. You understand?
Yes. Yes.
Further comments or questions?
You calculated together with Gianpaolo the next to leading order corrections to the BKP equation. You calculate the next to leading order corrections to BKP.
Yes.
You have cut contributions.
Sorry?
If you calculate the next to leading order corrections to the BKP equation, do you also have
next?
Yes. Just I'm talking about science fiction. Do you also get their cut contributions? Maybe Gianpaolo can answer that.
If we compute next to next,
yes.
Let's say that.
You're an expert on that. Do you have cut contributions at that order? Because everything is elastic there, no? It's always in the BKP you have elastic amplitude, and then when you go to next to leading order, there should be cuts in the same way as the ones described by Fadin here, or maybe I'm wrong.
No, probably you're right.
But was this calculation done, or Agustin, are you asking if it would be possible to? If you would go to next in BKP, yeah. The question is okay.
No one will do.
Okay.
Alessandro, if you stop the recording, then we can ask real questions.
Okay, let's close the official part of the seminar. And how to stop recording? Yes, this way. Okay, no.